A separator is a critical piece of equipment in the oil and gas industry used to separate different phases of a fluid. These phases can include oil, gas, water, and other impurities. After the fluid exits the well and goes through initial cleaning, it enters the separator, where the different phases are separated so that it can be sent to sales units or separate testing facilities. Separators are classified into three main types based on the shape and internal operation: horizontal, vertical, and spherical. A horizontal separator is suitable when the gas volume is high and a large surface area is needed for separation. A vertical separator is used when the gas content is low and controlling the liquid level is important. The spherical separators was more commonly used in the past and is effective for controlling oil and gas foam. Separators are also categorized by the number of phases they separate: two-phase and three-phase. In two-phase separators, gas is separated from oil, while three-phase separators separate oil, gas, and water. The internal design of separators ensures efficient separation, and inlet and outlet flows are carefully controlled. The inlet and outlet lines provide both flow management and safety. For instance, the oil line can be split into three passes, 1, 2, and 3 inches, depending on the flow volume. The water line typically has 2 passes, and the gas line is divided into 3 and 6-inch passes to control various flow rate. Operating temperature ranges from -20 Fahrenheit degree to +250 Fahrenheit degree, and the design is corrosion and pressure resistant. A three-phase separator is an industrial device designed to simultaneously separate oil, water, and gas, taking into account incoming flow conditions, internal pressure, and corrosive environments, including the presence of acetic gases such as hydrogen sulfide. This separation ensures the prevention of vortex formation, foam breaking, and proper operation of downstream pumps and equipment. Initially, the incoming flow passes through a deflector plate, which reduces its velocity, causing oil to fall downward while gas rises, achieving primary phase separation. Then the flow encounters the coalescing plate, which combines fine oil droplets into large ones, allowing them to settle more easily at the bottom and ensuring efficient separation. To separate water from oil, the flow passes through a weir, which operates based on the density difference between the two phases. Lighter oil gradually separates from water, and when its height exits the weir, it moves over the top toward the oil outlet, while water is directed through the lower section under supervisory control. The weir also helps smooth the flow, creating laminar conditions for more precise separation. Another key component, the vortex breaker, prevents vortex formation during oil and water discharge, which could otherwise disturb the flow and draw gas into the oil lines. Meanwhile, the foam breaker separates foam and gas bubbles from the liquid to maintain a clean, stable flow. Before gas exits, the mist extractor removes moisture and liquid droplets, ensuring particle-free gas flow and protecting downstream equipment. Finally, for inspection and maintenance, a manhole allows safe access to internal components when proper precautions are taken, including the use of safety masks due to potential hydrogen sulfide exposure. These manholes are designed in various sizes, such as 18 and 20 inches, to facilitate internal maintenance. Overall, all internal components of the three-phase separator are designed to efficiently manage incoming flow and direct oil, water, and gas to their respectively outlets safely and effectively. In a separator, observing and monitoring the internal liquid plays a crucial role, which is done through the sight glass. The sight glass allows the operator to directly see the level of water and oil inside the tanks and along the flow path. To ensure proper functioning, the sight glass must always be clean, which can be achieved by washing it with diesel or other suitable cleaning solutions. Adequate illumination is also essential, so a strong light should be available to clearly observe the flow inside the sight glass. During inspections, The outlet valves of the sight glass are carefully opened to allow the operator to monitor the liquid flow, and once the inspection is complete, these valves are securely closed. Any liquid drained from the sight glass is directed along predetermined paths to prevent contamination of the surrounding environment. Following these steps ensures that the sight glass provides continuous, safe, and accurate monitoring of the separator's internal fluids. Another important external component of the separator is the strainer, which filters out impurities, sediments, and suspended particles from the incoming fluid. The strainer is positioned at the inlet of the oil and water flow into the three-phase separator or the pump line to prevent clogging and pressure fluctuation. When necessary, the strainer can be removed, cleaned, and reinstalled to maintain proper operation. Additionally, in the gas outlet path of the separators, straining vanes are installed before the orifice method to reduce turbulence caused by elbow and twist in the flow path. These vanes help create a more uniform gas flow, allowing accurate measurement of gas flow rate. In some separates, the vanes are designed like gasket with holes to further minimize flow disturbance. Overall, the separator, through the combination of these components, including the sight glass, strainer, and straining vanes, safely and effectively separates the liquid and gas stream. Oil separates from water because of its lower density and float on top, while gas separates from oil when the pressure reaches the bubble point and to its lightness. Each stage of this process is carefully designed to allow the fluids to pass through the separator smoothly without causing damage to the equipment. One of the critical phenomena in separator operation is carryover. This occurs when some amount of oil, for various reasons, is carried over with the gas through the outlet layer. This can contaminate the surrounding environment and, in severe cases, such as malfunctioning safety valves or blocked lines, may even lead to a tank explosion. The causes of carryover are varied: lack of proper separator, incomplete well cleanup, nitrogen injection, the presence of fluid inside the separator, and increased oil inflow can all exacerbate carryover condition. Additionally, if the wellhead pressure is unstable or the fluid is suddenly diverted into the separator, the likelihood of carryover increases. To prevent this phenomena, it is essential to continuously monitor the oil level in the separator. This allows the well engineer to take necessary actions if the oil level changes. Sudden change in gas type or low pressure can also cause an increase in oil carryover, which must be carefully controlled. Another critical phenomenon is carry down, which occurs when some gas exits the oil outlet line due to a drop in oil level inside the separator. This situation disperses gas in the environment and increases safety and financial risks. The causes of carry down are similar to carryover, including lack of proper separator, increased oil viscosity, reduced oil inflow, and unstable wellhead pressure. When the flow is diverted or bypassed, the wellhead pressure remains relatively stable, reducing the likelihood of carry down. In some cases, when carryover or carry down occurs, to resolve the issue, the outlet of oil or gas is initially closed to prevent discharge, and then it is reopened to allow the fluid to exit the outlet lines. The degree of opening or closing these valves is determined according to the conditions and must be supervised by an engineer. Finally, if the fluid inflow to the separator drops significantly due to low wellhead pressure, the flow path is often diverted or bypassed to prevent the fluid from entering the separator. This ensures that the flow continues safely along a designed path. To replace an orifice plate, we first need to be familiar with the different sizes. Orifice plates start at 0.125 inches and increase progressively, with the largest size being 4.5 inches, as shown in the diagram. The appropriate size for replacement is selected based on the supervisor's instructions and can be changed if needed. But before doing anything, it is essential to check the number on the orifice to ensure we are using the correct piece. During handling and installation, we must be careful and avoid striking the orifice, as it can be damaged. Before placing the orifice into the daniel, make sure that the orifice bolt faces the upstream gas flow so that it is installed correctly. Then insert the orifice into the orifice holder, and before using it, apply grease inside the flow tube to ensure smooth and trouble-free installation. Following this sequence carefully not only prevents damage to the equipment but also ensures accurate measurements. To replace the orifice plate, keep in mind that the orifice is initially at the bottom. First, we open the equalizer valve and then open the sliding door arm. Next, we rotated the lower carrier arm until the upper carrier arm starts to move. Then, we rotate the upper carrier arm to lift the orifice. After the orifice is lifted, we close the sliding door arm and then close the equalizer valve. Next, we open the bleeder valve and loosen the top bolt of the daniel. Using the upper carrier arm, we lift the orifice and replace it. To place a new orifice back at the bottom, we first close the bleeder valve and then put the top seal of the daniel orifice in place, securing the bolts. Then we open the equalizer valve and open the sliding door arm, and we rotate the upper carrier arm to lower the orifice until the lower carrier arm starts to move. And next, we rotate the lower carrier arm to bring the orifice completely down. After the orifice reaches the bottom, we close the sliding door arm and finally close the equalizer valve. At the end, we open the bleeder valve and apply grease to daniel, and then close the bleeder valve. These are all the step-by-step procedures for replacing an orifice plate in a daniel orifice system. The data has fluctuations. Zoom shows that the points are not on a perfectly straight line and contain some noise. Zoom reset also confirmed this. However, the observed noise in neither severe nor unusual and usual has no specific cause, arising from measurement limitations. In later examples, we will see noise caused by physical factor that must be investigated. At this stage, no significant noise is observed and the data conditions is acceptable. Now, since all the data has been fully entered and checked, we are ready to proceed to the analysis section. At this stage, we enter the analysis tab and select the extract DP option. Since we have only one chart and one test, the production option is selected. We then confirm by clicking yes. This is for a gate or similar items that we do not deal with in this section, and press OK. The small sync section is not relevant here because I intend to work directly with the actual data, so we click OK again. At this point, both the pressure derivative chart and the pressure chart are plotted in log-log and similog scales. I enlarge the pressure derivative chart for better observation. Note that the very small noise we observed earlier in the history plot becomes much more apparent and precise when we view the pressure derivative chart. Even the smallest pressure changes, even if very minor, are displayed more permanently in the derivative chart. Thus, we see that any small variation in pressure has a significant effect on the dP per dt chart. An important point to mention here, in the pressure derivative chart, by right-clicking on the chart and enabling the additional derivative option, select the derivative of pressure with respect to time, dP per dt, to plot its curve. I now perform a zoom out so that the dP per dt chart can be observed more clearly. Keep in mind that whenever data contains noise, this chart should be plotted. In fact, I recommended always plotting the dP per dt chart to ensure that the data is reliable. The dP per dt curve should always trend downward. Whenever you see the chart trending upward instead of downward, like in this section, where it initially declines but at a point rises, this indicates incorrect data in that segment, meaning that data has abnormal noise. Therefore, to ensure data accuracy during analysis, always check the dp per dt chart. Its overall trend from start to finish should be descending. Any upward slope indicates data error or unacceptable noise. After this check, we disable the dp per dt and additional derivative options and proceed to the analysis stage. I enlarge the pressure derivative chart again for better visibility. Now, if we activate the special lines option, we can see that after the hump section of the chart, a slope of -1/2 appears, and the pressure derivative data falls precisely along this line. What does this -1/2 slope mean in the analysis? As discussed in the analysis section, this situation indicates Wellbore limited entry or partial penetration. Since there is only one region with this slope, not two separate regions, it is highly likely that part of the reservoir thickness has limited perforation. In the pressure chart, we see that it stabilizes up to this point. Showing the middle time region. But then deviates from the straight line and moves upward. This demonstrates that all three regions, early time, middle time, and late time, are observable in the data. Even in the history plot, before plotting the derivative, we noted that the reservoir boundary was visible and its type could be determined. In the similar chart, if we look closely, the early time region is visible from the start up to this point, followed by the middle time region and then the late time region. According to the analysis method, in the semi-like chart, by right-clicking and selecting the line regression option in the middle time region, where the data lies along a line with a constant slope, we select 2 points so that the permeability line can be matched. At this stage, we switch to the log chart and align the white line representing the model exactly on the yellow line, which shows the actual data. We then slightly reduce the chart size so that the details become more visible. The Wellbore storage section is also visible on the chart, but at this stage, our analysis does not focus heavily on it. Next, we return to the semi-log chart. After selecting the line regression option and identifying the slope in the middle time region, we choose the final slope and click on the results option. The software calculates and displays the results based on this slope and the scheme value extracted from it. For example, the slope is equal to the selected value. The permeability K is calculated to be approximately 41 millidarcies, and the scheme factor is obtained as positive 2.4. After reviewing these results, we click close and proceed to the next step, which is the model selection. The next model we want to discuss is the double permeability reservoir model. In this type of reservoir, we have two layers, as you can see in the schematic. The first layer has a higher permeability, while the second layer has a lower permeability compared to the first one. Now, because of this contrast in permeability, after production starts, a pressure difference develops between the two layers. The reason is that the high permeability layers produces fluid at a faster rate, while the low permeability layer produces much less. This imbalance creates a pressure gradient between the layers, which in turn drives a cross-flow of fluid from the low permeability layers into the high permeability layer. In this double permeability system, in addition to the well-known parameters omega and lambda, which are calculated by their respective formulas, a third parameter is introduced called kappa. Omega represents the storage capacity ratio, the fraction of pore volume in one layer relative to the total system. Lambda describes the interlayer transmissibility, which quantifies the strength of communication between the two layers. Kappa is a parameter that arises only in double permeability models, and it's calculated through a specific relation that accounts for the cross-flow process between the two layers. Unlike the dual porosity model, where only the matrix contributes to the fractures and the fractures delivered to the well, in the double permeability reservoirs, both layers are able to produce directly to the well. Typically, the layer with high permeability is denoted as layer 1, while the low permeability layer is denoted as layer 2. The crossflow between these two layers creates a transition region in the pressure derivative plot. Initially, at the early times, there is no pressure difference between the layers, so there is no vertical communication or crossflow. However, as production continues, the higher permeability layer depletes more quickly, generating a pressure imbalance. This imbalance causes the lower permeability layers to transfer fluid into the high permeability layers through crossflow. In some cases, there may be a semi-permeable barrier separating the two layers. In such situation, the transmissibility depends not only on permeability but also on the properties of this intermediate barrier. We denote its effective permeability and thickness by K' and H' respectively. The corresponding interlayer transmissibility lambda is then calculated using the specific formula that account for these barrier properties. If for any reasons lambda becomes equal to 0, no crossflow occurs between the two layers. In this special case, the system is referred to as a commingled system. Looking at the pressure derivative plot, we observe the transition region that corresponds exactly to the period when crossflow between the two layers takes place. After the end of the early time region, the transition behavior becomes visible, followed by the final stabilization line. Often, the very first flow regime is not clearly observed, and instead, the response begins with the transition period before reaching full stabilization. Now let us consider the sensitivity of pressure and pressure derivative plots to the model parameters omega, lambda, and kappa. When lambda increases, the transition period occurs earlier and the valley in the derivative curve shifts to the left. The reservoir also exits the transition region more quickly. On the other hand, for smaller lambda values, the transition appears later and it takes longer to exist this regime. Similar to the dual porosity model, smaller omega values cause a deeper valley in the derivative curve. With the small omega, the system enters the transition earlier but exits more slowly. With larger omega, the valley becomes shallower, the transition is delayed, and the system exits faster. The kappa parameters is specific to the double permeability model and controls mainly the depth of the valley in the transition region. The larger the kappa, the deeper the valley, and the smaller the kappa, the shallower the valley. However, kappa has little effect on the timing of when the transition starts or ends. It only controls the valley's shape. Therefore, in summary, the double permeability model captured both direct contribution of the two layers to the well and the vertical crossflow between them. The crossflow behavior is reflected as a transition valley in the derivative plot. Hose position and depth depend on lambda, omega, and kappa. Let's illustrate this with a practical example. Imagine we have three wells, well A, B, and C. Our aim is to calculate the pressure drop at well C. As we know, wells B and A also influence well C, and this effect must be included in our calculation. According to the principle of superposition, the total delta pressure at well C is equal to the sum of the pressure contribution from well C itself and from the other two wells. Expressed in word, total delta pressure at well C is equal to delta pressure from well C plus delta pressure from well B plus delta pressure from well A. For the pressure drop caused by well C, based on the solution to the diffusion equation, we have delta pressure at well C equals Pi minus PA well flow, which is calculated as 162.6 Q mu B divided by Kh multiplied by the logarithm of Kt divided by phi mu Ct Rw squared minus 3.23 plus 0.87 S. The pressure drop caused by wells B and A on well C is expressed as delta pressure contribution from well B and A equals negative 70.6 Q mu B divided by Kh EI negative 948 phi mu Ct RBC or RAC squared over Kt. A very important point in this calculation is the damage zone or skin factor. In our example, the skin of well C must be included in the equation, which is why we added 0.87 times the skin to the delta pressure of well C. The skin of wells B and A is not included here because their damage zone do not cover well C. If, however, the damage zone of well B and A is large enough to affect well C, the skin factor must also be included in the equations. Using the superposition principle, we can accurately account for the effects of multiple wells and the damage zones on the pressure at any well. This method allows us to perform precise and reliable pressure drop calculations, which is essential for real reservoir analysis and helps in optimizing production and injection strategies. By applying superposition, we ensure that pressure prediction in multi-well and complex reservoir and scientifically sound and operationally useful.